Itamar Vigdorovich, who's going to give the second introductory talk about Hilbert-Schmidt stability.
Thank you, Francesco. Thank you for all the organizers. It's very nice to be here. My first time in England, actually. Yes, I'll give an introduction about Hilbert-Schmidt stability. So this is, I think, already Gunnar a bit spoke about it. It's, in a sense, a counterpart to permutation stability, where you just work with matrices rather than permutations, but the type of metric, the type of problem, there's some similarity, I would say, between those two norms. Indeed, the Hilbert-Schmidt metric, in some sense, extends the Hamming distance, maybe up to a small error. So let's start here, and probably a good place to start is with this work of von Neumann from 1929. So this is like very old, where quantum mechanics was still kind of new. I took some quote, or at least I kind of perturbed the quote a bit. So the object of the present paper is the clarification of the relations between the macroscopic and the microscopic point of view of complex system. The main difficulty with reconstructing the Gibbsian macroscopic theory in this new quantum mechanics is that the tool of phase space. So you know, in physics you have this phase space, you have a position and you have momentum, and we consider that's the dynamical system happens in this phase space. But the phase space cannot be formed in quantum mechanics, since the position q and the corresponding momentum p are never simultaneously measurable. Instead, their probable errors are always related according to the uncertainty relation. We believe that the following interpretation is the correct one. In a macroscopic measurement of position and momentum, really two physical quantities are measured simultaneously and exactly, which however are not exactly position and momentum. So, basically, the microscopic, we have a macroscopic system, like a classical system. We measure position and momentum with no problem, yet there's the uncertainty principle relying. So he says, formulated mathematically, quantum mechanics attributes to the quantities q and p operators q and p, whose lack of commutability, which is h bar, corresponds to the lack of simultaneous measurability of these quantities. We now assume the two other commuting operators, q prime and p prime, exist, whose difference from q and p is so small that its size is characterized by numbers whose product does not significantly exceed that h bar, required by the uncertainty principle. The way I understand this, I try to read it, I read this paper in the last weeks to try to really understand it, is that what von Neumann suggests is that when we measure, we have now a macroscopic system of a lot of particles. When we measure position and momentum, what he suggests is that we're not actually measuring position and momentum. We're not actually measuring p and q, which is what we actually want to measure. We actually measured some p prime and q prime, which are only approximations of p and q, and that those p prime and q prime are actually commute, which allows us to actually measure them simultaneously. Okay? But of course, the question that needs to be here, just von Neumann just writes, suppose now that there exists q prime and p prime, and this is exactly, I guess, the topic of stability of the circumstances under which such exists. I want to now discuss this particular problem of almost commuting matrices. Now, I know this talk is about Hilbert-Schmidt stability, but I purposely want to start by talking by the operator norm stability, because I feel like you appreciate Hilbert-Schmidt stability and its abilities only after you see what is impossible to do in operator norm stability. So the example I'll take, I think, von Neumann, talks about infinite dimensional operators, but you could do the same relations in a finite dimensional operator. So let p, so n will be some integer that we fix. And we'll now consider two unitaries. So P will be a permutation matrix. And Q will be the diagonalization of this matrix. So if we diagonalize this matrix, what you'll get is 1 omega squared omega n minus 1, where these are the eigenvalues. Omega is e to the 2 pi I over n. This is sometimes called the Voiculescu matrices. And indeed, if you compute the commutator of PQ, and now I'm doing the operator norm. So this is the norm of PQ minus QP. But since since these are unitaries, this is the same as, if you want a more group theoretic version, is basically measuring this one. If you compute it, well, the best way, I guess, is to compute it is to actually conjugate, to write the P, bring it over here. Then you have basically this matrix, this diagonal matrix, and you compare it with just a shift of this diagonal matrix. Still a diagonal matrix, but just this. So what you get here is that this is equal to 1 minus omega, absolute value. And of course, this goes to 0 as n goes to infinity. You can think of this as the Planck's constant, in a sense, of this very small value. That's the lack of commutativity. Okay. So now, according to what we just saw, we're supposing that there should exist some p prime, q prime. So suppose exists p prime, q prime, which are in un, such that two things occur. One, these actually do commute. This is yeah. And the second is that delta, what was denoted there as delta p, and delta q are both, I would say, small in some sense, comparable to this h bar, or to this omega. So let's just say less than maybe a function of omega, of 1 minus omega, let's say. Some function, of course, that decreases as you go to 0. But I don't want to specify any quantitative aspects of it, because we'll show now that in this setting, such p prime and q prime don't exist whatsoever. Okay, so I'm going to give now an argument that I think there are different people who showed this result, basically, that there do not exist such p prime and q prime. This is Voiculescu, there's Kashdan. I'm going to give a very short argument by Excel and Loring that is very nice. It's actually, I think, a good introduction to what Marius is going to talk about and others about topological obstructions to stability, which is apparent in the operator norm. I'm going to give just the argument. It's a very beautiful argument, and it goes as follows. So suppose by contradiction, so we are supposing we'll reach a contradiction, and now we'll define, we'll interpolate between those p and p prime. So pt will be equal tp plus 1 minus t p prime. And similarly, qt will be tq plus 1 minus t q prime. Okay, this is, I think, a natural thing to do. And then we'll construct the following paths. So let's define gamma t. This is from 0, 1 to the complex plane. Gamma t of s will be equal to, now I'm kind of measuring commutativity in a sense between those two things. So I'm going to write s pt qt plus 1 minus s qt pt. And now I want this to be a number, so I'm going to take the determinant, this. Okay? So this is a path to the complex plane. Is this clear? What's the definitions before I say properties? Okay. It's actually a loop. Okay, why is this a loop? Because gamma, for any t, gamma t at 0 is the determinant of this thing. But the determinant is multiplicative or in any case, these are actually not unitaries, but what's important, the determinant is multiplicative. So when I reverse the order, it doesn't matter. So it's the same as determinant of pt qt, which is gamma t at 1. Okay? So this is a loop for any t. What other properties we'll want? What is gamma 0? So gamma 0 at S is when I plug in t equals 0, what we get is the determinant. Sorry, I am confused. Yeah. Did I confuse who's t and who's s, or? No, I think it's okay. What is gamma 0 of s? This is, yeah, this is the determinant of s times p0. What is p0 here? Where does it start? It starts at p. So it will be the determinant of pq minus plus 1 minus s qp. And the determinant, and gamma 1 of s is the determinant of s p prime q prime plus 1 minus s q prime p prime.
I think it's the other way around.
So which one did you do?
The primes are above and the non-primes are.
The not, okay, sure. Thank you.
Replace 1 with 0.
Thank you. Excellent. So this one is just constant 1. Right? Because p prime and q prime and q prime and p prime are the same. So it's actually the determinant of p prime and q prime, which are unitary, so the determinant is 1. So this is constant 1. It's just a constant curve. However, when you look at this one, if you'll compute it, once again, the best way to compute it is actually to bring this p to an inverse over here. And what you'll get is that this is 1 minus s plus s omega bar to the n. So what is this loop exactly? If I'll ignore this n, this is just a linear function. So it looks like this type of path. But then when you multiply it by n, if this is a complex plane, you actually rotate it n times, you'll get this loop, and you could show that it passes in particular over to the left-hand side. Okay? So what do we have here? We have here two loops. One of them is a constant loop at 1. The other one is another loop that goes around. And we'll get a contradiction once we show that none of those loops can pass through 0 by a winding number argument. So the last thing to note is that gamma t of s is never, oh, this is always not equal 0. And the way to show this, I'll say this as an exercise. Basically what you do, you look at this value here, and you use the fact that delta p and delta q are small to deduce that this thing over here is not so far an operator norm than pq. And this is a unitary, so if you're an operator norm somewhat close to a unitary, in particular you must be an invertible matrix. If you're an invertible matrix, your determinant never vanishes. So this is the argument by Excel and Norrie, which I think is very beautiful, especially how short it is. Okay. So as I said, what I really want to talk about is Hilbert-Schmidt stability. And now I want to just, I feel like this will show exactly where the power of Hilbert-Schmidt stability comes in. So let's go back to these matrices. I'm going to define now p prime and q prime, which will satisfy these two things. So what will be p prime and q prime? So let's start with let's start with p prime. So assume for simplicity that n, this is now I'm going to give you an argument by So let's assume for simplicity that n is a square. If it's not a square, do the exact same argument, but you'll have some residue to what I do, which will be small and won't matter. So when n is a square, I can now divide my matrix to blocks of d by d. Now in each block, what I have here is some permutation. I have this 0 all over the place with 1s here. So this is not really a permutation matrix, right, because it ends, but I want to now close the loop. What I'm going to do is now close the loop. So there's this 1 appearing here. I'm going to erase this 1, and I'm going to put this 1 over here. And then I'm going to do the same thing here. I have 1, 1, 1, 1, 1, 1, 1. I'm going to erase this 1 and put it over here, and so on. So now I have blocks of permutation matrices, d by d, d blocks of d by d permutation matrices. What I'm going to do here is also split it into blocks. What I'm going to do, I'm going to erase, at each point, here I have omega to the d, or, yeah, omega to the d. I'm going to erase all the entries. I'm going to take the first entry and I'm going to just copy it all over the entries. So here I'm going to get 1, 1, 1, 1, 1. And here I'm going to do omega d, omega d, omega d. And here I'm going to do omega 2d. Now, let's see. Doing this is really harmless because all I did here, there was the worst case scenario is this entry here where it was omega to the power of d minus 1. So all I did is change the entries at most by omega d minus 1. So even in operator norm, I didn't change here much. I changed everything by at most omega d minus 1, which goes to 0 because d is much smaller than n. It's a square root of n. So it's omega to like square root of n. Here it's actually crucial that we use the Hilbert-Schmidt. Here I did something much more violent, right? I just took a 1, I erased it, and I moved here a 1. Thank you. Here I did something else. I took this 1, I erased it completely, I moved it over here. And operator norm, this is very much not allowed, but in Hilbert-Schmidt, this is allowed. Okay, maybe I'll recall just the definition of Hilbert-Schmidt, just that it's clear. Now, X is a matrix. This is the trace of X star X. And now we always normalize. You can do a non-normalize, you'll get a different variation of the problem. And you take the square root. This is the Hilbert-Schmidt norm, the normalized Hilbert-Schmidt norm. You can work, if you work with coordinates, if this is an actual matrix and you check what this is equal, what you get is this is 1n sum over ij of x ij squared. Or if you prefer in a spectral way to write it, you take all singular values counted with multiplicity, so, and you take the singular values squared. And finally, there's one more definition that I think is nice, which is somewhat more geometric or probabilistic. You apply your matrix to a vector, and you measure the norm. Now, when you do operator norm, you take the maximal possible way, the maximal number you achieve. What you do here in Hilbert-Schmidt is you take the average norm. So you do a norm, and you take an average here in the unit sphere. And you take a square root. Okay? So these are different definitions of Hilbert-Schmidt norm. And with all of them, you can see that what I did here didn't change much. The last thing maybe I should have said is that these two matrices commute. Because these are just diagonal, these are actually scalar on each block. And this is in the same block structure as this. So definitely this and this commutes. So this is Glebsky's solution to showing that these matrices, which in operator norm cannot be corrected to commuting matrices, in Hilbert-Schmidt norm they can be corrected to matrices. And actually what Glebsky then shows is that any two matrices, not necessarily these examples, any almost commuting matrices can be corrected to commuting matrices. Okay, so any questions regarding this? Okay. So let's now give just the definition of a Hilbert-Schmidt stability, and I purposely wanted to give a definition which is different than the definitions Gunara gave, even though they're all equivalent, but this is just a different way to state things. So definition, an asymptotic representation is a sequence of a group G, is a sequence pi n of G into finite dimensional unitary groups, dn, such that the homomorphism law that you need to check occurs. I should write here, this is for, I should write quantifiers, this is not good, I did it, such that for each G and for each H separately, you'll get that this norm converges to 0. And then you said that G is said to be Hilbert-Schmidt stable if whenever you have such an asymptotic representation, you can find another sequence of representation, pi tilde, such are close. And once again, this is for each G, this norm goes to 0. Of course, we're not, if you require some uniformity, you could play that game, but you get a completely different one, different definition. Okay, and this definition, it's, when you write it like this, of course, this is, here it's actually clear that it's a group invariant if you define things in this way. It's just something about the group. But I guess the fact is that this is equivalent to a definition that you would write if you use relations, a presentation of the group, generators and relations. Okay, so now I'm going to give examples, and I tried actually to give all the results I know about Hilbert-Schmidt stability, but if I missed anything, so please let me know, because I probably missed a few. So I'm going to split between amenable groups and non-amenable groups. So as for amenable groups, we have the group Z to the D. This is Glebsky's result, which I mentioned before, that is Hilbert-Schmidt stable. That's almost commuting matrices are close to commuting matrices. And now, right before that, just to say that maybe this example was quite easy to show, but once you take now general matrices, Glebsky actually works, it's not like extremely hard, but it's not a trivial fact to show that when you have two commuting matrices, you can correct them. And therefore, this is what makes the following theorem so powerful by Hadwin and Schulman. It says the following. An amenable group, so it's only for amenable groups, this theorem, an amenable group is Hilbert-Schmidt stable if and only if any character of G is a limit of finite dimensional characters. So before I'll say what is characters, I guess just the appreciation of this theorem, I guess, is, okay, character is some notion for harmonic analysis, somehow a notion that kind of you can handle, and that this very hard problem of Hilbert-Schmidt stability for amenable groups actually has a very kind of relatively checkable thing that one needs to check. So maybe I'll say a bit about characters. Maybe I'll say first, what is a finite dimensional character? So what are finite dimensional characters? These are something which you're quite familiar with. So when you have a group G, you represent it into a finite dimensional unitary group. This, of course, lives inside this algebra. And this algebra has the trace. And I'm going to take the normalized trace. And when you compose this, you get this function phi, which this is what I mean by a finite dimensional character. A function that arises in this way. When you do infinite dimensional characters or general characters, the idea is as follows. You have a group G, and now you have a representation, a unitary representation, not necessarily finite dimensional. And then this lives, of course, inside bounded operators and H. And what you would want to do is now take the trace, but of course this does not exist. There's no linear functional on B of H that one could feel good about and calling it a trace. But actually what we're not actually trying to take the trace of all bounded operators, we just want to take traces of operators that come from the representation of G, right? So what you do is that you bypass this as follows. You look at the image of G as a subgroup of U of H. And now you look at the algebra that this generates inside B of H. And of course, because now we're doing infinite dimensionals, when you take the algebra, you definitely want to take some closure. And the closure that we're going to take here is, in a sense, the biggest closure, a very big closure. So this is the weak operator topology. So this is called the von Neumann algebra of the representation. And now you have a von Neumann algebra, which usually in the study of von Neumann algebra, you're very much interested if this von Neumann algebra admits a trace or not, or does not admit a trace. If it does admit a trace, in fact a faithful trace, this may exist or may not. But if tau exists, we say pi is tracial and define phi to be the composition of the trace with pi. So this is the definition of a character in general. Of course, if your representation is finite dimensional, you're contained into a matrix algebra, which definitely has a trace. So all finite dimensional characters are characters. So now revisiting this theorem, I forgot to write if and only if there, but it's also important to note that this is really an if and only if, is that for amenable groups, all you need to check is whether all those characters, those coming from infinite dimensional representation, whether you can approximate them in the pointwise convergence topology. It's a discrete group, and you have the pointwise convergence topology, and you check whether every character can be approximated by finite dimensional characters. So just an immediate corollary that you get from this is that virtually abelian groups are Hilbert-Schmidt stable. And this is something that would be very hard to prove without it, and it's completely trivial with it. Because virtually abelian groups, all unitary representations, all irreducible unitary representations are finite dimensional already. There's not even something to approximate. All the characters are finite dimensional. So with this theorem, it's actually completely trivial. The virtually abelian groups are Hilbert-Schmidt stable. Definitely abelian groups. That's Glebsky's result, where all characters are one-dimensional. And also you get here for finite groups, which for finite groups, I guess you don't need, you can do something on this line, but a bit easier, but still, so even for finite groups, it's not something that is easy to prove that finite groups are Hilbert-Schmidt stable. So this includes all those examples. I thought maybe saying something about the proof of this result. Maybe I'll just say, maybe I'll say something about the proof. So this will be very sketchy, of course. But let's do the easy direction. The easy direction is to show that if you are Hilbert-Schmidt stable, then every character is a limit of finite dimensional characters. So you start with a character, phi, and this character, by definition, comes from a representation pi. into it lives inside some von Neumann algebra, M, and there's a trace here. Now, because the group is amenable, this whatever von Neumann algebra you get is what's called Konzi-bettable. So it means that you can approximate this von Neumann algebras by subalgebras. It's kind of like like a Sophie group, just the analog notion for von Neumann algebras. So basically, what I'm saying here is that this representation, I can find finite dimensional representations here. Finite dimensional almost representations. Because it's kind of like the almost representation. We're looking for approximate finite dimensional approximations that converge to pi, converge in a sense that the corresponding traces converge to phi in the pointwise topology. Now, these phi n are not exactly characters because pi n are not actually representations. They're almost representations. But now, if you have stability, you actually know that you can change them into pi n tilde and take this to be phi n tilde. Now, I'm a bit cheating here because you might get something in a different dimension, but this is basically the idea. The other direction is deeper and it uses... Sorry?
So this is with this direction without amenability.
It is with amenability in the sense that I'm using that I need this M to satisfy Kahn's embedding problem. This is where I use amenability. If you know that you took a group which is not necessarily amenable, you chose a representation, you got some phenomena and you know for some reason that it satisfies Kahn's embedding problem in the sense that you can approximate it by finite dimensional, then you can do the same. So me and Lalonde have a formulation which we used for higher rank lattices where it's not amenable, where there's some you can formulate something completely general for groups, but you'll need to just formulate things very carefully about which characters you can approximate, which not, etc. So yeah, the other direction will be you want to show stability, so you start with almost representations pi n. And this is actually similar to what Gulnara talked about, that all Sophic approximations of amenable groups are equivalent, are conjugate to each other. The analog here would be Kahn's theorem, which eventually implies that all matricial approximations of von Neumann algebra are all equivalent. So basically, if you have if you want to prove stability and you have now almost representations, you take some kind of limit, and then you use a limiting character, and then you'll take that use that property to have a limit of a sequence of actual characters converging to it, and that will be the correcting characters. But to say that they're actually close, that's where you need Kahn's theorem. Okay, so after virtually a billion groups, the next result is about nilpotent groups. Sorry?
Strict stability or only flexible stability?
Everything is in strict stability, but because of the same arguments, flexible and strict is the same thing for amenable groups. You can always add some trivial representations if needed to correct for things. In the amenable cases, doesn't really. Everything is really flexible here in the sense you do it, and there's no difference. The next result is about nilpotent groups. So all finitely generated virtually nilpotent groups are stable, and this is really amounts to studying characters of nilpotent groups and showing that this satisfies this property. Now, this whole character theory is something which was very popular starting in the 60s. It was advocated by Thoma as kind of a way to do harmonic analysis on an abstract group, rather than studying unitary representations, which is notoriously hard and in some sense impossible. One studies characters instead, and since then there were a lot of results about characters of nilpotent groups, etc. But of course there's more to do in order to get this approximation property. Another thing, once you continue inside solvable groups and you go beyond nilpotent, you very quickly find yourself in very deep dynamical problems. So this happens quite naturally, that you have a group G, and you have a normal subgroup here, N, and suppose it's abelian. Our group is, let's say, solvable, and you take this abelian normal subgroup. And now you want to understand characters of G and ask whether there are limits of finite dimensional characters. At some point or another, you're probably going to take a character of G, you'll restrict it to N, this abelian group, and analyze that. And what you'll naturally get to is this following dynamical system, G acting on the Petrarchian dual of N. So for example, if this is Z semi-direct product Z to the D, you'll find yourself with a transformation of the torus. And then the question of whether characters are approximated by finite dimensional characters will correspond to the question whether invariant probability measures of this dynamical system can be approximated by ones that are supported on finite sets. So we have this prob X, some space of invariant measures, and inside of this you have the finitely supported invariant measure, in other words, orbit measures, and you ask whether this is dense, whether you can approximate anyone here by someone here. So in some cases, one can, after you go to this next problem of dynamics and you start analyzing dynamics, sometimes you can get a result. So for example, with Ari and I managed to show is for the Lamplighter group, for example. So for the Lamplighter group, this is the group, it's a wreath product, so Z mod 2Z, and Z acts by shift. So the dynamical system you'll naturally find yourself analyzing is, of course, the Bernoulli shift. And by analyzing the Bernoulli shift, it's not very hard. It's basically what's called the orbit closing lemma to show that finitely supported invariant probability measures, which are basically come from sequences which are periodic, approximate any invariant probability measure. And this is how you show, this is part of the argument why Lamplighter groups are stable. Baumschlag-Solitaire groups, I would say the argument is similar, but this is Baumschlag-Solitaire, not like the one was discussed there. This is a much more simple group. It's a metabelian group. And another example is Z semi-direct ZD. By analyzing dynamics on torus, you can get similar results. More than the positive results, I think it's where it became very related to deep problems is once you consider a bit harder examples of groups. So take, for example, Z squared semi-direct product ZD, or the example Z squared semi-direct product Z1 over 6. And here I need to give you two automorphisms of Z1 over 6. So one of them will be, of course, multiplying by 2, and the other one will be multiplying by 3. And if you want to understand whether this group is stable, you must understand Furstenberg's times 2 times 3 system, if you know what that is. And similarly here, what you need to analyze is two commuting automorphisms of the torus. Now these problems are considered very hard, and there are a lot of conjectures between them. For example, the biggest conjecture is what's called measure rigidity, which tells you that the only invariant measures you'll have are in some sense the obvious ones. So you'll always have the Haar measure on the compact group you're acting, and you'll have finite measures coming from rational points usually. And the conjectures usually say that under certain assumptions, these are the only ones. If you would know that these conjectures were true, you would get stability. Because if you know that all the measures are either already finite, or the Haar measure, which definitely can be approximated by the finite orbit measures, then you would get the criterion, the dynamical criterion you need, and you would get that they're stable. But of course, it's weaker than that. It's like asking, here's a question which might not be as hard as Furstenberg times 2 times 3. It's just asking the following: is every invariant measure of Furstenberg times 2 times 3 approximated by orbit measures, by finitely supported measures? Very recently, Rotem Yari, that's Aria's student. You have a question?
It's there is clear that there is no implication, that if every measure is approximated, then you have classification? Like it might be.
You're asking if it's clear that there's no.
Or
I would say the following. There's another conjecture that you can, I think it's sometimes attributed to Elon Lindenstrauss, of equidistribution. And this says that if you take any sequence of finite orbits, they will weak star converge to the Haar measure. If you know that, then they become equivalent. I would say there are two basically hard, there's like three different questions that you can ask that are all interconnected in a way, but I wouldn't say that, yeah. Rotem Yari recently had a very nice paper where it's very dynamical, the paper. So really considered here A could be now any group. And considered one automorphism, so Z semi-product A, and managed to show that such groups are always Hilbert-Schmidt stable.
You mean any abelian?
Of course, yeah, sorry. Of course. A means abelian. Which is quite nice because it sounds very hard to do dynamics because you don't, like you look at A hat, so what can A hat be? But apparently there's a very nice theory that tells you how it could be in some sense composed from tori or selenoids and some profinite groups that you act on. There's a very nice theory there that can be studied. What Alon, Ari, and I showed, we considered diagonal products. It's a nice group construction that gives you a wide range of groups, and already before people use those groups to create large variations of certain properties. What we showed is we introduced this notion called stability radius, and I think Henry Bradford will also talk about this. Which basically saying, okay, there's two quantitative versions that you can ask for stability. One is what's called usually rate, which is really what's the connection between this delta and epsilon. But there's something a bit subtler that is apparent more in infinitely presented groups, which we call stability radius. So basically you have an almost representation. Assume you know your group is stable. So it means once you look at this finite ball, and you see that things are acting almost multiplicative, then you know that you can correct it. But you can ask how big that ball needs to be, rather than the connection between delta and epsilon. How big in the group you have to look, such that if there it's almost multiplicative, then you're actually close to multiplicative. So this is what we call stability radius, and what we showed using diagonal products that it could be arbitrarily bad. So the group could be stable, but it could be extremely hard to detect that it's stable. In particular, this shows that there are uncountably many such, because you can take any function in the world. I'll take a group, even like a non-commutable function. I can take a group that has with stability radius worse than that function. So the question that arises naturally from here, after so many groups are amenable, and I think it was open for a while, is whether all residually finite amenable groups are Hilbert-Schmidt stable. Residually finite is definitely necessary to say here, and this is exactly because this robustness application. If you have a group that is both Hilbert-Schmidt stable and amenable or sulfic or hyperlinear more generally, and maybe assume finite generation, then the group has to be residually finite. So you have to remove, and indeed it's easy to construct examples that are not residually finite. And then very recently, Caleb Eckert showed that the answer is no. So constructs very concretely certain upper triangular matrices, linear groups, solvable in particular, that are even finitely presented, if you wish, that are not Hilbert-Schmidt stable. And again, using character theory and even using some of this dynamics type of thing. Basically, you need a dynamical system that doesn't have that property, that every invariant measure is a limit of finitely supported measures. One last thing that is kind of hiding there, but of course all those questions become extremely harder. Take the easiest examples here and just start asking quantitative questions. The questions become much harder. These sometimes are more interesting for computer scientists. And specifically, for example, MIP star equals RE contains a long proof of stability of the finite abelian group Z mod 2 to the power of n, but of course they actually need quantitative and strong quantitative estimates of this. So there's also the work of Michael de la Salle, which systemized it, but in the end, it's about quantitative results of this sort. Now I'll talk about non-amenable groups. So the first example is, of course, free groups. So actually, when you write it, okay, whatever definition you use for amenability, if you use generators and relations, so of course, if you have no relations to satisfy it, there's nothing to say. Everything is homomorphic. So of course, free groups, and more generally, if you take free products of stable groups, you easily see that this group is stable. Extensions of this include, first of all, Grisimova's and Chepin's virtually free groups. So this followed Ariel Levit and Nir Lazarovich's work in the permutation setting, where they use the fact that virtually free groups are a graph of groups, are the fundamental group of graphs of groups of finite groups. So H and N extensions and amalgamated free products of finite groups. And indeed, there were following works about other amalgamated free products, but usually when the amalgam is normal, sometimes finite, etc. A result by Johanna and Spa says that if you take, this is kind of like the product question, which we already saw that it's the product, that stability doesn't go into products, but however, if one of the groups is amenable, then stability does pass to products. So for example, the group Z cross F2 is Hilbert-Schmidt stable, despite it being not permutation stable. Johanna has a very nice work where product of free groups are never Hilbert-Schmidt stable. This was also mentioned before. So if you have a group with property T, and the group is infinite, then it is never Hilbert-Schmidt stable. But when you look at the proof and you understand why, what you really realize is why the notion of flexible stability is the right notion in a sense of stability. So basically when in the definition of stability here, note that I require, here's the almost representations, and the correcting representations are all in the same dimension. But there's really not a good reason why you have to correct it in the duration. Maybe you can correct it in some larger dimension. And then you just need to ask, how do you compare two representations of different dimension? But you do, in a sense, the most natural, you embed matrices into larger matrices in some natural way, and then this will allow you to compare these two matrices. And that's how you get flexible stability, by allowing this. So indeed, when you see the proof of property T groups, you realize that really the idea is to start with something of a larger dimension, erase some things in order to go to a lower dimension, and then say, oh, now you cannot, like the representation you want to correct to is the one you started with, but you're not allowed to because you have to stay in the same dimension. This is why flexible stability is so natural.
But what does that arrow to flexible stability mean exactly?
So flexible stability means that
I know what that means, but what do you mean by arrow flexible stability?
this gives rise to the notion of flexible. Okay. One thus considers flexible stability. Johannes Spass and Wiersma, they have a very nice paper about cohomological obstructions. It's very much relating to the lifting property, which will be talked about later. But regarding stability, it follows from their work that the group SL2Z, semi-direct product Z squared, is not Hilbert-Schmidt stable.
So what about groups with property tau?
Excuse me?
What about groups with property tau?
Tau instead of T? So if you do TFD, in the sense that spectrograph over all finite dimensional representations, everything works perfectly well. If you have property tau, I don't think so, but here's a question, is property tau and TFD equivalent for residually finite groups? I don't know of a counterexample for that, and I think it's a question by Alex Lubotsky and Robert Zimmer, whether these are equivalent. But TFD is the right notion here. connections to hyperlinear groups. So this is the Hilbert-Schmidt version of what Gunnar spoke about, is called robustness. So if you have a finitely generated hyperlinear group, so hyperlinear group means that you have some asymptotic representation, which is also asymptotically injective. So you can approximate your group by matrices, basically. Every SOPHY group is definitely hyperlinear, but not vice versa necessarily. So if you have a group that is hyperlinear, so there exists some approximation, and it is stable, means that you can actually correct that almost representation to representation, you get that your group can actually be represented faithfully into matrices, and then by Malchev you can get also to permutations, to finite groups, and that's how you get residual finiteness. So indeed this could be a way, for example, this is one connection to hyperlinearity. But other connections arose later as follows. So Alon Dagon proved that for once you have a group with, I did just one version here, but if you have a group with property T and a non-vanishing cohomology and a bit of extra assumptions, but what's nice is that it does work for random groups, for example. If you show that the random group with positive probability is stable, there exists a non-hyperlinear group. This non-hyperlinear group will be a central extension of that group. What me and Alon showed recently is managed to show that this group, which has a big advantage because this group is an amalgamated free product of two stable groups. Right? SL2Z is virtually free, SL2 is both of them are virtually free, so actually when you have you can always correct for each copy separately. The question is, can you match the corrections together? And we wrote a very concrete problem relating to this question, which I like to advertise because it's somehow very concrete and could give either a non-hyperlinear group, but even showing that this group is not stable, this is also will solve a question whether higher rank lattices can be stable or flexibly stable. Lastly, I'll just say things about variations of this problem. Something you can, of course, mix different norms. You can take operator norm on one side and that you're allowed to correct with Hilbert-Schmidt stability. Or I think Mario's talk is going to be very much about that. You can talk about unnormalized Hilbert-Schmidt norm, but that gives you a completely different problem, sometimes called the Frobenius norm stability. I think Forrest will talk about that. Rather than unitaries, you can ask about Hermitian and normal operators. If you study C-star algebras and stability of C-star algebras, there's no really, reason to restrict yourself to unitaries. These are also very natural questions. Rather than taking only finite dimensional matrices, you can take von Neumann algebras and do the Hilbert-Schmidt norm there. This is called W-star stability sometimes. You can discuss local stability where you don't actually correct to a representation, but you're not even required to restrict a representation, but only to a local representation, which means that multiplication really acts as you wish, but just on a large finite set, not on the whole group simultaneously. This is an older result by Dogon and Akhtiamov, where you discuss uniform Hilbert-Schmidt stability. So Hilbert-Schmidt stability, but where, okay, it's more like Ulam stability, if you know what that is, just in the version of Hilbert-Schmidt stability. These happen to be all virtually abelian. You can talk, and rather than everything in the Hilbert-Schmidt norm, you can call it the Schatten 2 norm. But you can take the Schatten P norm for every P, you'll get other questions, also studied. Hyperfinite stability. This arises naturally when you take, so there's a notion called weak stability where you only require to correct not all almost representations, but only the ones that are hyperlinear approximations, only the ones that are asymptotically injective. Here it's the same thing, which actually in a different way, that these are only, you only need to correct almost representations that are in some sense hyperfinite, and one way to define it is that at the limit they generate a hyperfinite von Neumann algebra. This arose naturally because for higher rank lattices this problem is equivalent to character rigidity in a way that is in spirit similar to Hadwin Schulman's work. And this is more a joke than anything else, but the point is that there's embarrassingly a lot of notions that you can talk, and there's much more, and it's really not clear yet what are better notions, which are worse notions, but UCP stability and weak stability, I said, and you can talk about very flexible stability, but the idea is here that there's really a lot of variations that you can play around. I'll just finish with some open problems. One very basic problem is whether it passes to finite index subgroups, this property, in general, in both directions. Okay, this I thought to say, I kind of actually said everything I want about this one, but there's just a lot of deep, if you're interested more in dynamical aspects, there's a lot of deep questions over there. Surface groups, while in the permutation case, as mentioned, it was solved at least that there is flexible stability. For Hilbert-Schmidt, it's still open. Right-angled arcing groups, it's very natural after Johanna's result about F2 cross F2. And we know abelian groups, so you can consider, for example, the pentagon as the next example and ask whether that is stable. And of course, higher rank lattices we know nothing about. No example, no positive or negative example of course, flexible Hilbert-Schmidt stability. And specifically, this example, which is probably the most basic one to consider. And you can get a lot of mileage also by considering that one. That's it.
Thank you, Itamar. Are there questions?
Yeah, so you talked about flexible stability. So you said you first increase the dimension and then you correct there. How much do you increase the dimension?
Sublinearly, like
Sublinearly.
yeah, like in a way which is dn over dn prime, which is the new dimension, should tend to 0.
Okay. Would it make sense to go from dn to 2dn?
So that's already called, like, if you don't do any restrictions, you would call that very flexible stability. The problem is that it's a bit less natural. It sounds like very natural, but when you think about it, I like to think of it as I have a representation. I'm looking for a sequence of almost a representation. I want to find other representations that when I compare them in the natural way, it goes to 0. But if one of them, the dimension is much higher, then there's already automatically a big error, in a sense that in the natural way you could define it. But I think there's something a bit more natural about flexible when it's sublinear. But yeah.
But is it much easier to prove this very flexible thing than?
So so Tatiana, in the amenable case of maybe all groups are very all residually finite.
No,
you don't even need residually finite.
All amenable
groups are very flexibly stable. I don't know about beyond the amenable groups. Yeah.
But I think there is a observation of Johanna that when you go to finite index, very flexible is okay, but the other is not. So there is a difference.
So if you want to show that stability passes to finite index subgroups, and you do one of them might be very flexible.
Right.
It's
So
good
there
pass.
is a
Okay.
difference. Yeah.
I see.
Yeah, for number 2, you have a test, simplest test candidate that you can deal with.
First number times 2 times 3.
That's the simplest one.
Oh, simplest in the sense of something that I don't know how to solve.
Yeah,
But
like say Z3 with 2 commuting actions. Do you have a
no, Z3 specifically, Z6 with 2 commuting actions. I have an excellent
I mean,
example. But
okay.
like torus, 6-dimensional torus. I don't think in dimension 3 you have room for 2 commuting automorphisms, but in dimension 6 you start having very interesting ones. I have me and Ari have a very particular example that, for certain reasons, is very interesting to understand, because actually that we tend to think that doesn't have that property, which would give, but there, for torus there are a lot of interesting examples. What?
Matrices come from Katoks.
Yeah, matrices come from Katok. The reason is because those 2 matrices are not hyperbolic matrices. They're what's called ergodic, which is a bit weaker. And it's exactly where the classification conjecture, the rigidity conjecture does not hold. So you can have, or at least not in its simplest form, you suddenly have an exotic invariant measure. Not very exotic, it's just coming from a circle for the fact that you rotate around the plane and you have this circle measure. And we believe that you cannot approximate that circle by finite. you believe, one believes that usually that the finite ones will equidistribute and they won't all be around this one-dimensional measure. So that, yeah, that's a very particular interesting example, I would say, and maybe not extremely hard, but I don't know.
More questions?
I have one more. What do you think about polycyclic groups? Do you think they will all be Hilbert-Schmidt
No,
stable?
so I think that this example of z-squared semi-direct product z6, I think you can have that. Maybe that's an example of something, a polycyclic group that is not Hilbert-Schmidt stable because of no dense periodic measure. And permutation, of course, they are. Yeah, so that would be also.
More questions?
Do you have, I guess at this point you don't have a meta-abelian group, which is not Hilbert-Schmidt stable, right?
A metabelian group, and you want residual finiteness, I guess.
But sorry, they are all residually finite, right? That's the point.
No, they're always no. What I meant to say is, I guess, finitely generated. No, I have examples which are not finitely generated. But if you're asking finitely generated metabelian groups, I think there's no known non-example of Hilbert-Schmidt stable group.
I think it might be that.
So the question whether all finitely generated metabelian groups are Hilbert-Schmidt stable is equivalent to the question whether every dynamical system of commuting automorphisms on a compact abelian group has the property that every invariant measure is a limit of finitely supported measures. It's equivalent. The two problems are completely equivalent.
So that this is, I mean, the question for permutation stability for metabelian is also open. Either one of them would give the original results of I think it was Philip All who proved that every meta-abelian group is residually finite. What's interesting that the method he used were of kind of commutative algebra by geometry, not really within classical group theory. So it would be beautiful to add a second flow from other directions.
More questions? And let's thank Itamar again.